All right, so if there's no other, yeah. Okay, cool. So number 10, the one little thing with number 10 real quick is when you see this means barely above 0. So basically treat it as 0. So it says groups of 5 babies are randomly selected. In each group, the random variable is the number of babies with green eyes. So the instructions for this is determine if a probability distribution is valid or not. And if it's valid, actually figure out the mean and the standard deviation. So how do you check if it's valid? 0 through 5. And they have the probabilities here. Okay. So it's groups of 5 babies, the number of babies with green eyes. So to have all 5 babies have green eyes is a very small probability, which sounds right, because there's not a ton of green eyes. It's mostly blue and brown. So how do you check if it's valid first? What 2 things have to be true to show that it's a valid probability distribution? What are the probabilities supposed to do? That's to add up to 1. And be between 0 and 1. So cool. So they all look between 0 and 1. This guy's just barely above 0. He's cool. So they're all between 0 and 1. Do they all add up to be 1? What is the sum of these probabilities? It doesn't have to be exactly 1, by the way. Just like when we did our histograms. When we did our relative frequencies, it depended on how much we rounded. And I don't know what the 0 plus is exactly. It's normally something less. To be more precise, it's something less than this. So it could be 0.004. Right? That could fill in something I'm missing. But when you add them up, what do you get? Just about 1? When you say just about? That's all right. So when you add these up, you get what now? You get 1? Sweet. So maybe this is like crazy tiny. It could be this at most, but it could also be 0.002. Right? So it sounds like it's valid then, because all the probabilities are between 0 and 1. The sum of them is 1. So then now you have to attack this thing and figure out the mean and the standard deviation. And when you do that, you just treat this as 0. We basically just confirmed that it is almost 0 anyway, so we just treat that as 0. So this might be a good thing to do real quick on the overhead, just in case it sounds like there were people that weren't here. So you would probably be well served by seeing one of these things in action. Someday, whenever this thing warms up. So we'll do this little review of 5.2. We'll do this problem like it's a review of 5.2. There's a couple little things I got to finish out in 5.2. If you've done the homework, has anybody hit the expected value questions yet? All right, so I've got to talk about that a little bit. Expected value, when you... how many guys have car insurance? Have I already talked about this? Mm-hmm. The magic day when you turn 25 and you suddenly know how to drive, supposedly, because your insurance premiums go way down. I still remember that day. It was a really good day. Because every dollar then, I was in grad school and I was living, plastic life, really putting everything in credit card just to make it through. And I'm like, any little bit of money I can save is good. So how do they determine those numbers? They do probability tables. What's the probability for this age group that would pay out this much, pay out this much? And then they try to cover themselves by making everybody pay a certain amount that on average will more than cover how much they'd expect to pay out. Does that make sense? Because they want to make a profit. So we're going to figure out what's the bare minimum that they have to do to make a profit, and then we're going to charge a little more just to verify, just to get that profit. You guys kind of with me? I mean, so they do these probabilities. So the probability that somebody over age 25 will be in an accident is lower than somebody under age 25. And then, of course, once you get up higher, then all of a sudden it goes up a little higher again, because then you're one of these people. Maybe. You ever seen those people? Oh, yeah. I try to stay away from that. Oh, what's going on? Nothing against them, but it's just a little scary.
Sometimes you don't want to drive near them.
No. All right, one of these is a computer. There it is. All right, so let's do this problem together real quick. So please, on this homework set, if it's not a valid probability distribution, if the sum of the probabilities is 0.8 or something, don't figure out the mean and standard deviation. They don't mean anything for that then. If it's not valid probability distribution, if it's not a valid probability distribution, don't do the work. You know, I am a very patient teacher. Some of you guys probably disagree with that, but I think I've been told I'm a pretty patient teacher. But I lose all my patience doing that. So if you ever see me in a post office line, I'll be majorly antsy. My friends have given me little toys to play with in case there's a traffic jam, because they've ridden with me in the car. So they're like, let me give you something to do, Jeff, because I go a little crazy in traffic jams. It's not a good area to live in for that.
Probably good you run on the 52 this morning then?
Yeah, I heard about that. There was some giant accident.
Really bad accident.
Yes, I heard about it. I was a few streets over, thank God. Sorry if you were there. Okay, so to do this problem, you get into your lists. This is one way to do it. This is the way I would do it. And then you put in there your x's 0, 1, 2, 3, 4, 5. You put in there your probabilities. We're just taking this all from number 10. Of course, 5 we're going to treat as 0. And you can check real quick. You could do, you can come out of here, you can go to second stat, go to math to sum up. List 2, that's where all my probabilities are. And I do get 1. So that's cool. So that looks good. What do I want L3 to be? So here I got my x, I got my p of x. Bless you. What do I want L3? Here's L1, here's L2. L3 is going to be what? X times p of x. Cool. So that's what it is conceptually. And then, of course, what's it going to be? What do I want to tell it to do right now? L1. Yeah, L1 my x's times L2 my p's, right? L1 times L2. And that's all on that handout I gave you. All right, cool. So you do L3 is L1 times L2. And then what I want list 4 to be to kind of get what I need to eventually do the standard deviation, because the variance is this guy. So I need these. So of course I want this column to be that. I need a bunch of these to exist before I can actually add them up. So like I told you, when you get one of these equations with the summation symbol, you just cover that and you go, oh, I need these. Okay, let me get a column of those so that I can do what it tells me to do, add them up. All right, if you can add numbers that aren't there, you are neat. So let me make sure the numbers are there first. So what do I want L4 to be then to make this happen? Yeah, you could do L1 times L3, I love it. You could also do L1 squared times L2 to get x squared p of x. I don't care, it's the same way, either way. L1 times L3, there's my x times x p of x, which gives me x squared p of x. And there's those. Right. Where's my mean come from?
L3.
Beautiful, L3. It's going to be the sum of x p of x. Or write better one. No, I don't know what this is. So if I add those up, and how do I add those up really quickly? Let me show you this. Here's what I would do here. I personally, to tell you honestly, and I know I've told you to do this, I personally hate going to second, stat, math, sum. If you can handle what I'm about to do, this is a much quicker way to do this. I eventually need to add what two things? What do I need to add up? To get the mean, I got to add up L3. To get the standard deviation, I need, a part of it needs the sum of L4. So I need two pieces that I need to sum. Let me show you how to do this very quickly. If you go to stat, calc, one var, don't do one var stats, do two var stats. Because now I can do two columns at once. So you guys can handle this. If you can't handle it, just do your sum like you have done in the past. Go to two var stats. And what did you just told me L3 and L4. So let me tell it L3, comma, L4. Now it's going to give me a bunch of crap that I don't need. What's the only thing I need from that list of stuff? The sum. The sum of this is 0.599. Cool. And if I scroll down, here's the part that we haven't seen yet. It'll tell me, since L3 it says X, what do you think this thing's going to call L4? Y. There's the Y's. So the sum of L4 is 0.885. That's the sum of X squared P of X. Now if you don't like what I just did, that's fine. You can go to second, stat, get in your list, go to math, sum L3, and then sum L4. Who cares? I just want to real quick show you another way to get those quickly. So my average is this. How to get my standard deviation now? What do I have to put where? Yeah, so I got the mean. I just got the mean squared. The mean is 0.599, so I need to square that for that piece of it. And what number goes here?
0.885.
Yeah, that's the sum of these. That's what that is, 0.885. And that's the variance. It's really fat when I stand over here. So you do that difference, and then how do you get the standard deviation? Just take the square root. So the variance is always the middle step, right? And then you take the square root to get the standard deviation. Cool. How you guys doing? I love it. You guys, most of you guys are like, okay. Whatever you say, Jeff. All right. And again, looking at the list itself, would you say, now this is kind of weird. The data is not this. The data is this, right? Why do I say that? If I had 1,000 numbers, can anybody tell me how many twos I would have? I would have 98 twos, because this is 98 out of 1,000, right? How big is my list that I'm working with? I have no freaking idea. I know that 0.098, 9.8% of them are twos. You kind of with me? All right, that's what that really means. So notice, if you look at this, does it make sense? That's going to come out pretty damn small. I don't know if everybody's calculated that yet, but your standard deviation should be pretty small. Why does that make sense? Because where are most of my data? Most of my data is where? 0. Over half of my data is 0. 36% is 1. I mean, does the data really vary much? You got a bunch of freaking zeros, a few less ones, and then almost no 2s, 3s, and 4s. So that standard deviation should be crazy small. It doesn't get very far away from this really small average. Why was the average so freaking small? Because there's so many freaking zeros. Right? So it's a good idea to, can you make sure that this makes sense? The numbers you're getting, do they make sense?
Would you mind just going over the bar stats one more time?
Sure.
Just what you entered.
So the fact that I want the sums of these two columns, so I go to the calculator and I say, calculate two things at once, two var stats. Calculate two var stats for L3 and L4. Calculate the statistics for those two lists. And it tells me more than I need, but that's normally fine. I want more than I need than less than I need. So I just pick out exactly what I need, the sum. Now something that might wake some of you guys up, because I think some of you guys are in like a little bit of a, just took a stats quiz trance right now. There's an ultimate shortcut here that you are allowed to use to check yourself, but you're not allowed to. I love it when I say show work and somebody says, I press this button, and then I press this button.
Congratulations.
But here's the ultimate shortcut. If I do stat, and how many variables are really up here? Remember, this is all about babies and green eyes. How many variables are up here? There's one variable, right? There's number of green eyes I see. That's one variable. You with me? So I should be able to tell it to do calculate one var stats. But remind me, where is my data? Where's my data up here? List 1 and list 2. This by itself is not good enough. How many zeros do I have? I don't know. Not one. This tells me how many zeros I have. This tells me how many ones I have, so forth. So I can do one var stats, but here's the freaky thing. I tell it L1, L2. I tell it look at both lists. So if I do one var stats L1, L2, does that look familiar? There's my 0.885, there's my 0.599. But n is 1, that really means that it adds to 1 like it should be. The probabilities add to 1. That kind of kicks ass a little bit, right? And those of you who actually finished this out, hopefully you got that. After you did the subtraction, you did the square root, there's your standard deviation. That is way cool. A way to check yourself very quickly. Not good enough for work, but good enough for checking.
The sum squared when you do 2 var stats L3, L4 would be different than...
Hell yeah, definitely.
Okay. And it should...
Because when I do 2 var stats on L3, I'm just doing 2 var stats just because I want to do 2 columns at once.
Okay.
So I'm letting the calculator think that there's 2 variables, but I just want to get the sum real quick. That's why I was hoping, that's part of what I was hoping you guys would understand. I'm just doing 2 var stats just because I want to do 2 columns at once. That's the only reason. I really do just have one variable, the green eyes. Cool. Okay, how we doing? So those hopefully should not be horrible, because they give you that handout that kind of spells out exactly how to get through this stuff. There are 2 things I want to talk about real quick from 5.2, and then maybe I can get into 5.3. One is that expected value thing. And, you know, if I said that there was some deal I could get involved in, it was people wanted me to invest some money so they can build some store downtown. You with me? It's going to be everything is $6.48 store. Right? They got all the freaking other denominations. Why not? So if the economy, let's say the market gets better, this deal would give me $40,000. I would profit $40,000. You guys with me so far? This sounds like a real life problem. If you got money, you can invest it, and you want to look at your risk. Right? Anybody ever seen that movie Along Came Polly? Right? That was Ben Stiller's job, was assessing risk. So he's using a lot of what we're doing right now. If the market stays the same, then I'll make $8,000. If the market gets worse, I'll lose $50,000. Okay. So this is all risk assessment. Right? This is what really good poker players do. They assess their risk on every turn, and they play for the long run. They might lose a few tournaments, but then they'll win big if they play a certain way. This is what people that make investments do all the time. This is what insurance companies do all the time. All I need now is to know the probabilities of each of these things that might... what are the probabilities of these things? What I've got so far that I can put together is I've got 40,000 is one possible outcome, 8,000 is another outcome, and how should I be careful about writing that last guy? Negative $50,000 is the third outcome, right? So now I just got to know the probability. So let's say the probability the market gets better is 20%. Probably stays the same. Let's say is 60%. So probably gets worse is the last 20%. Is that cool? So now I got my x's, I got my values, and I got my p of x's. I just gave them to us directly, right? 0.2, 0.6, 0.2. So now we just attack it like we just did. We get our XP of x. And the really funky thing, the nice thing is, I don't have to get the standard deviation here, thank God. Expected value, another name for expected value is mean. The mean is the expected value. If you had to make a guess, you would guess the mean. That's not a bad idea. Right? And the really cool thing about that is, what's the formula for the mean in this case? The sum of xp of x, and look how it says expected exp. Can you beat that? The math formula itself is a note. The mean is the expected value. So when they ask for expected value, they're really saying, find the average, find the mean. So how do I do this? I just multiply those out. 2 times, you can do it, Jeff, I think it's 8, no, you can do it. Yeah, 8,000, 4,800, and this will be negative 10,000. You can check me if you want. So this comes out, if you add these together, you get 2,800. So what does that really mean? If I do a bunch of deals over the long run, a bunch of deals like this, I can expect to make $2,800 on average each time I do it. So if this number comes out positive, it's good. You should go ahead and do that. If it comes out negative, that means you would expect to lose money. Basically, every game in a casino is negative expected value for us, so that the casino is making money. Sure, that guy over there just won $2 million, but there's 3 million other people, they just lost $1. So the casino's like, cool, man, go ahead and win. Just brings more people. Listen to that, people are winning, let's go. And they give you free drinks, so your judgment goes down and all kinds of neat stuff. So when they say find the expected value, that's all they're saying. Do XP of x and add them up. You don't even have to do standard deviation. You've got the expected value. So if there's another deal at the same time, and its expected value came out to be $4,000, of course, which deal should I do? Which deal is better? Yeah, this one. It's got more money you should expect to make, right? Is it a guarantee you're going to make that? Hell no. This is all probabilities, dude. But you play the odds. You go with the way that's going to be more definite. Maybe. Okay. All right, and let me think. There's one other thing I can't remember. Oh, that's right. Let me ask you this. Would it be unusual to be walking down the street and see somebody who is 7'4"?
Yes.
Yes. Obviously, that would be unusual because it's so. Now that we know some statistics, we can be even more precise about this. What would really tell me that was unusual? What could I calculate? Yeah, the z-score, the number of standard deviations away. But we kind of have a feel for that. We know internally. We've internalized the math. We know that would be freaky, right? Because we know that would be way up here on the end of the normal curve. And the other reason why it's unusual is because it's got such a low probability for something in that area to happen. Now, the reason I say in that area is it would be unusual for somebody to be exactly 68.12993466293333 inches tall. Wouldn't it be unusual? But when I say his height is unusual, that's 5'9", basically, right? Is that an unusual height? No. So when I say what's unusual, you actually have to think about the area it's in. So the reason that the 7-foot tall dude was unusual is because it's in an area with such a small probability. That area. Here's a 7-foot tall dude, and the probability that it's 7 foot tall or more is so small. But here's the 5'9" dude. He's right in the middle. His specific height is unusual if you want to go that specific, but he's in a normal area. He's in an area with high probabilities. That's not unusual. How are we doing, sir? Is that all right? A little bit. So that's going to become more pronounced later. They do make a little point of that in section 5.2. Okay. So now, in the little bit of time we got left, I want to at least introduce the ideas in 5.3 and 5.4. And section 5.3 has this weird-ass formula that if you have a teacher that just gives you the formula, you're going to be like, all right, I'll plug shit in there, but I have no idea why this is anything. And you know me by now. I don't do that kind of shit. I tell you all the backstory. Because the more you understand what a formula is supposed to do, the more you'll use it correctly. You put the right stuff in there. Okay. So here's the idea. If I pick 5 people, and let's say the probability of somebody, I don't know, what do I want to say? That somebody likes Brussels sprouts. Anybody here ever had Brussels sprouts? All right, still brings back nightmares from when I was a little kid. And I'm probably still finding Brussels sprouts stuck under the carpet in this place. But probably somebody likes Brussels sprouts in general. Let's say that's 20%. So a problem I would have asked you before section 5.3 would have been, what's the probability that the first person likes it while the last 4 don't? Right, that sounds exactly like something I just had on that quiz. It's probably the first 2 agree and the last 2 don't, or whatever. Right? And this is the Hangman Game. This is where we can control what probabilities go where. So I want the first person to like it. So what's that going to be? 0.2. And then I want the last 4. First guy likes it and the last 4 don't like it. So what's going to go in those places? 0.8. So of course the smarter way to write that really, instead of doing all this, is how many 0.2s do I want? 1. How many 0.8s do I want? 4. So there's a more concise way to write it. Thank God math people came up with that. In case we have 80 people. I want to write this forever. And then do that real quick for me. What's that come out to be if you do that?
0.08192.
0.08192. Okay, cool. So we'll say it's about that. Roughly 8% chance. Okay, how are we doing so far? That's a question I could have asked you on a quiz if I really felt like it. But here's the difference. Now, can anybody spot the difference between that question and this question? Some people don't immediately see the difference. Because they look here and they say, well, Jeff, you had one person liking it here, what the hell? But there's a very specific thing about this that differentiates it from that situation there. There I want exactly one of them to like it. And here I want the first person to like it. So what? Is that the only way that exactly one of them can like it?
No. There's a chance in each of those.
Yeah, well, in fact, help me list the ways. The first guy could like it, and the last 4 not.
Yeah.
Or
The first one could not like it. The second
maybe the second one likes it, or maybe the third one likes it, or maybe the, is he actually going to do this? Yes. 4th one likes it, or maybe the 5th one likes it. So this is only talking about that first situation. And notice what word I kept using that's important in probability. It's this way, or, there you go. What's or mean? Add. So I really want to add up all these probabilities, because what's the basic idea of probabilities? I want to bring in everything that matches what I'm looking for. And what matches this is not just this, it's all of these. And what does each of them look like algebraically? If I wanted to write it in a better way like this, wouldn't this first one be L times L to the 4th? Is any of them different from that? Of course they're all the same, because every single one of them wants exactly 1 to like it. And how many of them do I have? 5. So if I add this to this to this to this to this, I'll end up with 5 of these. Now, is that ground-shaking, earth-shattering, amazing stuff? No, it's not. But when you see the formula for this, for when I get more complicated stuff, do I always want to make this list? I could very easily make this a list that I would never want to work with. Here, I've only got 5 situations that could happen, right? What if I said exactly 3 of them likes it? That would suck. Because it could be the first 3, or the first one in the middle 2, or the first one in the last 2, or the first one in the last one and the second one. And so then that list would get a lot longer, and it'd be really easy to leave one out. Right? How are we doing so far? So real quick, before I get away from this would be 5 times the same number we got here. Is that cool? Because this is this. We calculated that here. So 5 times that is roughly 0.4041, just about. So what, in general, did we just do? If it was 5 people, and I want exactly 3 of them, to like the Brussels sprouts, to like BS. Just real sense. What would they each look like? I don't want to make the list, because the list would be long. I don't know if everybody really understands that, but that list would be long, and it'd be really easy to leave somebody out. Because there's so many ways, the first 3, the last 3, the first 2, and the last one, and there's so many ways to do that. But what would they all look like? How many of each of these would you have? How many of these would I have? 3. And how many of these would I have? It's got to be 2, because I got 5 total people, right? So for example, just show a couple examples. It could be the simplest way would be this. There's 3 people like it. Or it could be, you can do it, Jeff, that. There's 3 people like it. And that list would be a lot longer than that list. But they all look like this. So what's the only thing that I gained? What's the only piece here that was good because I can make the list that I can't get here right now? What's the only thing I'm missing? I could count this list, right? So what was this 5 again? Because there were 5 ways to do it. How many ways is there to do this? I don't want to do that list. Shut up. I don't want to do it either. So thank God there's a couple of keystrokes in the calculator that'll give it for us. And this is one place where I let you just get this thing straight from the calculator. And really the idea here is I've got 5 spots. I want to choose 3 of them to put L's. You guys with me? How did I make these lists? I chose 3 spots to put L, and I put L not in the rest of them. So that's kind of nifty. So I got 5 spots. I want to choose 3 to be L. And the rest of them are going to be L not. They're going to be don't like it. So here's the math. So I don't know if everybody's kind of with me here. I got that 5 because I could count the list. Very nice short list. And I knew they all looked like this. If I just had some quick way to tell how long this list would be without actually having to make the freaking list, because sometimes it's millions long. Screw that. And there is. And here's where it is in the calculator. So if you do this, you do 5, and this is why it's really cool, because the way we say it in English is actually the way we do it on the calculator. 5, math, PRB for probability. Number 3, see that big C? That stands for choose. 5, choose 3. So it's not long as all hell, is it? It's just twice as long. But it would be really easy to leave somebody out. Sure. So 5, math, PRB for probability. Number 3 is choose. Don't worry about National Public Radio here, number 2. Number 3 is choose. So 5, choose 3. So there'll be 10 things. And if we try to make the list, we'll probably get 9 or 8. It's really easy to miss somebody. So real quick, just to show you, if I had 7 people and I wanted to choose 3 of them, now it's up to 35.
It's exponential.
Worse than that. And if I had, 20 people, and I wanted to choose 3 of them, now we're up to 1,140. So thank God we have that method. In the book, just to be careful, so this is the way I would write it up here, 5, choose 3. In the book, they have this formula. Oh, that's the formula they use in their formula for this section. We're not going to use that formula. Right? In fact, some of you guys are like, why are they having exclamation marks in that? That exclamation mark means if I had 7 factorial is what it really is. If I had 7, that's 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what that means. So we're just going to do this. We're going to replace that part of the formula with this keystroke combination in our calculator. All right, so we'll pick up there next time. I obviously just barely got into 5-3. Just don't freak out if you don't understand what the hell's going on yet.
I remember having to do those by hand.
Oh, yeah?
Uh-huh.
Oh, yeah.
I don't miss it.
I don't blame you.
I like to go back in time and tell my younger self about TI-80.